m-
Hi,
Friday,
Dad. I was
my
going to
happy
call and see if
hour.
I would get to welcome again, but I
I
see
think
somebody
somebody
saying,
needs to be muted.
okay, thank you. Bye.
Okay, so welcome to the Friday Happy Math Hour. We're gonna talk about today the set theory, basic property of sets, complements, subsets, and Venn diagrams. So let me get started. So the first thing that I want to mention is what is a set? So in mathematics, a set is usually a collection of objects or a group of objects. And these objects, they may have anything. They could have numbers, they could have letters, they could have, we can represent maybe a set that has cars, a set that has chairs. So it could, when we say objects, it literally could be anything, not just numbers. These objects are called the elements of the set. And the way that you see before, so it is telling us that a set can be described in different ways. Because it has objects, one way would be what we call the roster method, which means you just create a list. So usually when we say like, oh, the roster of people, we refer to the list of everybody that is part of the group. So similarly, you can list each one of the elements or at least a good amount of them so that it's clear what elements are in that set. So that is the roster method when you create the list. We also have the set builder notation, which you see on the bottom. And the set builder notation usually has, this one focuses on describing the set. So if you look at the example below where it says membership conditions in blue, and then we have brackets, anytime that we have sets, we need those brackets, by the way. Whether you're using the roster method or the set builder notation, if you don't have those special, I call them the curly braces, if you don't use those brackets, then it's not considered a set because it gets confused maybe with an interval of numbers or something else. So to represent a set, we need that special notation. And then we have a variable x, and x represent a typical element. Then we have a vertical line that we call that vertical line, it's read as such that. So we're saying like this set has the elements x such that they satisfy the conditions that are on the right. In this specific example, the condition is that x is an element of the natural numbers and x is greater than 7. So this set builder notation is a very algebraic way of determining sets by describing the properties that each one of them has. So this is an example. You could also give a word description of a set. Notice that in example A, we actually have the set of all. This would be, how would you describe this set? We have this set before I give you the answer. Notice that the set is listed right now. It's in raster form and it shows A, B, C, D, E, F, all the way until the Z. If we wanted to make a word description, a way of saying this would be A is the set that contains all the letters of the English alphabet. And this is actually this is actually the word description. Now, in example 2, it says write a word description for the set, and then we have the curly braces, and then March and May. Well, a word description for this set would be, this is the set of names of the month that start with the letter M. So these are the months that starts with the letter M. And that kind of makes sense, right? Because those months would be March and May. Notice this set B is the third and the fifth month of the year. So basically, that could be like another way of describing. We could say like the set B has the third and the fifth month of the year. So this shows you that a word description, there may be possible, there may be different ones. It doesn't have to be exactly the months that start with the letter M. So whenever you have a set, you might have more than one way to describe it. The next one, this slide shows you the basic number sets, the typical number sets that we deal almost in all of our classes, and it is kind of like it has a, each set is actually bigger than the previous one. So the smallest set, this is the set of which is the top one. We call it natural numbers or the counting numbers. I notice that this set is denoted with the letter N for natural. And then we have like 1, 2, 3, 4, 5. And here we're using the roster method, but notice that we put the dot, dot, dot. This is also common because we know that numbers are infinite. I could continue going to 100, 1,000, 10,000, and so a million, a billion, so on. I would never finish if I wanted to list all of them. So often for these special sets, we use those three dots. That mean it is an infinite set. It contains all of the numbers that are greater. I always tell my students, like, following the pattern, like one by one, increasing one at a time. So the next value would be like 6, 7, 8, and so on. The next category is the whole numbers, represented with the letter W. And notice that in this set of numbers, it's pretty much the same as the naturals. It just contains an extra number, which is 0. And the way that I like to kind of like help my students remember is by saying that natural numbers, these are things that you can represent physically. Like you can have maybe 1 pencil, 2 chairs, 3 cell phones. So these are things that you can represent physically. And the 0 number is not something that we really have a physical. In fact, whenever we say like, oh, how do you represent 0? We always say, well, it represents nothing. Like, oh, I don't have a car, so that's 0 cars. Or I don't have children, so it's 0 children. So the whole numbers is basically the natural numbers plus 1 extra number, which is the 0. The next one is the set of integer numbers, which includes all of the whole numbers, so the previous ones, all of the previous ones, plus all of the negatives. So on 0, we add -1, -2, -3, -4. And notice also the dot, dot, dot. So this set is infinite in both directions. There's infinitely many numbers, many negative numbers to the left, and infinitely many numbers negative to the right. So the next set is the set of rational numbers, which we represent with the letter Q. And the set, you could think about a way of describing this is the set of all terminating or repeating decimals. So when you have a number, you can write it in decimal form. And the rational are the ones where this decimal form terminates or ends, that it only has like two or 3 or 1 decimal. An example of that, if you look before, I have written a few examples below, which is 1/2. If you put that in decimal form, that is 0.5. But notice how it ends on 5. There's nothing to the right. And then 4, all of the numbers above, all of the numbers before, all of the integers, all of the whole, and all of the natural, they're all considered to be rational numbers as well. Maybe something less predictable would be like 1/3. So 1/3, if you put it in decimal form, it's going to be like 0.333, and it's supposed to be infinitely many threes. And I always like to remind the students, if you put a fraction in a calculator, usually the calculator only displays a certain amount of digits. But often these fractions are infinite, so they're supposed to continue just 333 infinitely many times. And the reason why this is counted, so even though it doesn't terminate, it doesn't have a finite amount of digits. The other condition is if it's a repeating decimal. So the fact that it's the same 3 repeating many times, that makes it a rational number. Another example would be like 0.37, and if you guys recall, the line above usually means that these repeat. So like 37, and then 37, and then 37, and it just continues infinitely like that. So these repeating, usually these repeating decimals, they're infinite decimals, there's infinitely many digits, but they have a repeating cycle. So in this case, the cycle would be 2. And you can have a lot of these numbers. all of these numbers actually have the property that you can write them as a fraction. That's why at the end it says P over Q. So the set of rational numbers can also be thought as the set of all numbers that can be put into fractions. And if you were wondering, like, what are those numbers that you could put into fractions? Well, those numbers are the ones that the decimal terminates or it has a repeating cycle. The next set of numbers is the irrationals. These are a little bit more rare. And these are numbers that are all non-terminating and non-repeating. So there's infinitely many decimals and there's no repeating pattern. An example of that would be pi, because pi is like 3.1415, and then it continues 9 to 6. I only wrote up to 6, but there's actually infinitely many more decimals that continue, and there's no pattern. It's not like you could say like, oh, every 5 the 1 repeats. It seems like it's just random numbers that are coming out. So and pi is a very special number, but you actually, to get easier examples of irrational numbers, you can think of, for example, most of the square roots that cannot be simplified, the square root of numbers, like square root of 2, square root of 3, square root of 5, square root of 7, all of that, if you put them in the calculator, you'll see that they fill out the entire calculator and it doesn't have a repeating pattern. Okay, and last, the real numbers is supposed to contain all of the previous ones. So one way to make that combination is by saying that the real numbers are all of the rationals and all of the irrationals. The irrational numbers are very special, and in a sense, they're kind of rare. Even though there's a lot of those, they're infinite. There's infinitely many rationals, but the most common ones that we deal, they're rationals, because the rationals contain all of the integers, all of the whole, and all of the natural numbers. Okay, so let's continue with our discussion of sets. So you can represent a set by using the roster method. So in example, say A, it says the set of the days of the week. Well, in roster method, it would be by listing each one of the days of the week. Notice how each element is separated by a comma. When the students do this in WebAssign, they always ask me, like, does it matter the order? Does it matter if you leave a space between them? None of that matters, but what it does matter is the commas. Because if you didn't have commas, it's like you have a big long word. It's like just one object. So each comma separates the different objects, the different elements in the set. So the commas are necessary. And of course, the curly braces need to be at the beginning and at the end. So the next one is the set of months that starts with the letter A. And these are the months of August, April. So this is a set that contains August and April, and it's only 2 elements because there's only 2 months that start with the letter A. The next example, it says use a roster form to represent the following set. So the set of natural numbers less than 5. So remember that on the right, you can see the set of natural numbers. The natural numbers or counting numbers, these are the ones that you can represent physically. So starting with 1, 2, 3, 4, and so on. And the ones that are less than 5 would stop at 4, huh? We don't include it. So it would be only 1, 2, 3, and 4, because it says less than 4. If we have like less or equal, then you can include the 5, but less than 4 should stop at 4. Less than 5 should stop at 4. Okay, so the next one, which is B, it says the set of negative integers greater than -4. And again, you see the list of the of integers. Integers contains all of the positive numbers, the negatives, and 0, which is neither positive nor negative. And notice that B is supposed to be negatives greater than 4. So I always like to remind my students, like, if you don't know which one is greater and which one is less, the greater number is always to the right. So when you look at this list, -4 is actually, it's greater than -5. But notice that it says greater than -4, so -4 should not be included. It should be like the next one. Well, the next one, the next number that is greater than -4 would be -3, -2, and -1. And even though 0, 1, 2, and 3 are greater than -4 because they're positive, any positive number is greater than a negative. Because it's saying negative integers, then I need to stop at -1. So the answer for this would be -3, -2, -1. Something that have, so it seems like you have many ways of representing sets and many ways of looking into sets. And something that we need to be careful is a set well defined? How do you know can you create a set just by using any word description? For example, is the set the set of letters of the English alphabet? Well, this is actually a set that is well defined because you can determine each of the elements that are in the set. So if I mention the set of English letters of the alphabet, you automatically think of A, B, C, D, all of the letters. So you know exactly what's in there. And in B, which is the set of great songs, well, if I were to ask you what is the set of great songs, then this is something that cannot be determined specifically, that we can all get the same answer, because a great song is something that is subjective. Maybe for me, a great song would be a specific song that I heard, maybe a country song, and someone else would say, well, I like this other pop song. And so defining what is a great song or what is a good song, it's something that is subjective. We all of us not get the same answers. Therefore, set B is not well defined. So you could say, like, there's not a standard method for making a judgment of which song is a great song or which one is not. And this, in comparison to example A, the set of the letters of the English alphabet, this is well defined because everybody know exactly what the elements are. So that's how do you determine if it's a well-defined or if it's not. So definitions regarding sets. So this symbol, we actually saw it before. It looks like an E, but it's more like a Greek symbol. And what that symbol means is an element of. So this symbol is used to differentiate between an element and a set. So by using it, we're kind of like saying, like, this object is an element of this set. And if you put a line cross like a diagonal, then it's the opposite, like this object is not an element of the set. And so the example says, determine whether each statement is true or false. So in mathematics, when we put these symbols together, they represent statements, and you can actually tell if it's true or false. So for A, if I translate it into words, and this is an exercise that I always ask my students, like, hey, can you read it in English? What is this? What are all of these symbols telling you? What it's saying is the number 5.2 is an element of the set 1, 2, 3, 4, 5, 6. Well, this statement is false, huh? Because the set 1, 2, 3, 4, 5, 6 has only like integer, or has only like whole numbers. There's no decimals. So 5.2 is, so this is actually something that is false, because 5.2 is not an element, so you should have the other line crossing. Let me see if I have the answer. So that one's false. And then B, it says -101 is an element of the integer. The I represents the integer. Remember that the integers are like all of the positives and all of the negatives and 0. Well, because this is a negative whole number, I'm going to say, yes, this is true. And C says 2.5, it's not an element of the whole numbers. Well, the whole numbers, like every time I think of the word whole, it means that it's complete. So there should be no decimal or fractional parts. And so this is true because 2.5 is not a whole number. So this statement is true. Saying that 2.5 is not a whole number is accurate. So in letter D, we have the set of nice cars. And again, to begin with, I would start by saying, like, we don't even know if this is a well-defined subset, because which one are if it's a well-defined set, because how do you know which ones are like nice cars? Again, that would be something that is subjective. So more definitions. So sets are similar, that kind of like numbers, and just like numbers, we have operations and we have a special sets, such as like these symbols represents the empty set or null set, and it's actually both symbols. Like one of them looks like an O that has a line crossing, and the other one is just the two brackets and nothing inside. So this is kind of like the equivalent to the zero. So there's a set that is empty. There's nothing inside. So the set of natural numbers that are negative integers. So this is an example, because natural numbers are supposed to be, by definition, starting with 1. And when you say the set of natural numbers that are negative, it's like you're combining naturals that also are negative. Well, there's no elements, there's no numbers that are natural and negative. So this is an example of an empty set. Another method of representing a set is the set builder notation. We kind of like mentioned that at the very beginning. And this is what it looked like. So I kind of described very briefly before that you're supposed to, inside the brackets, you're supposed to make kind of like an algebraic description. So you always start with a variable. This variable may change. It could be whatever you want to. So X represents an element. The vertical line is read as such that. So whenever you see that line, you're gonna read such that. So you're saying X such that X is an element of the naturals and X is greater than 7. So examples of using the set builder notation. In A, we have the set of integers greater than -3. Well, you can write this. I think this is pretty similar to the one that I had. So it's X, remember to put the brackets and then vertical line such that X is in I, because the I represents integers, and you want to write that and, because it has an extra condition, not just any integer. It has to be greater than -3. So in set builder notation, this is how you write it down. So X such that X is an integer and X is greater than -3. Okay, and so B now, it says the set of whole numbers less than 1,000. Well, pretty similar. I just need to remember how to represent the set of whole numbers. And the representation is by using the W. So it will be X vertical line such that X is in W and X is, and here the symbol is wrong. It should be less than 1,000, because the statement says less than 1,000. So just the symbol should go on the other direction. Okay, so definitions regarding sets. Other definitions related to sets. So we've talked about an element. We've talked about the empty set, which is a special set. Other definitions are such as, what is a finite set? A finite set, well, a set is finite if the number of elements is in the set of whole numbers. So in other words, the quantity that it contains has to be a whole number. And the cardinal number of a finite set is the number of elements in the set. So this cardinal is kind of like saying, like, how many does he have? Well, we're going to represent it by the letter N and then parentheses. So it's at the very end. The cardinal number of a finite set is denoted or represented with the notation n parentheses a. And we have an example. What is the cardinal number for the set below? Well, we just need to see how many elements are inside that set, which is, if I count them, would be like 1, 2, 3, 4. The last one is 9. So the cardinality or the cardinal number would be 4. So you count it, and you could represent like n parentheses a equals 4 because there's 4 elements in there. And so this is a finite set. This is an example of a finite set because the cardinality is a whole number, which is 4. Find the cardinality of each of the following sets. So for A, how many elements do we see? Well, there's 2. So you could write down n parentheses j equals 2. For the next one is a little bit more tricky. Part B actually shows S, which is 3, starting with 3, 4, 5, 6, 7, and then we have the 3 dots, which is called the ellipsis. So the ellipsis sign. Remember that the ellipsis sign, it indicates it continues on that pattern. So if you look at the previous one, the pattern was like increasing one at a time. So the next one would be like 8, 9, 10, 11, so on until you get to 31. Well, how many does it contain in here? A nice trick to count this is that if you had the whole list of numbers, like if you count 1, 2, notice that B is actually missing 1 and 2. But if you add them, it would be like 1, 2, 3, 4, 5, 6, 7, and go all the way till 31. Well, the numbers would be counting themselves. So it would be from 1 to 31, there's a total of 31. And so because this set is actually missing the 1 and 2, then it would be 31 minus 2, which is 29. So that is always a nice trick of counting. Like if you add the elements that are missing, you can know what is the total, and then you subtract those ones that are missing. So the cardinality of the set S, which is n parentheses S, is 29 because there's 29 elements or objects, or in this case, they're numbers. There's 29 numbers in that set. The next example, letter C, it has T that has 3, 3, 7, and 51. So the cardinality of this set is, interestingly, is actually 3. So, and this is one of those things that I always like to explain to students by saying that by definition, a set is completely determined by the elements that it has inside. So if we look at example C, even though the 3 is repeated twice, the different elements are only 3, which is 3, 7, and 51. So when it comes to set, when you repeat elements, when you repeat objects, they're only counted once. It doesn't matter how many. Because if I were to describe it in words, I would say the set T is the set of 3, 7, and 51. So it doesn't matter how many times they repeat it, there's only 3 different ones. So the cardinality is only 3. So in a way, you're supposed to kind of like simplify the set by deleting one of the 3s. And in WebAssign, often when it asks you to write an answer, you're not allowed to repeat them because WebAssign will kind of like tell you that it's wrong because it's implying like, hey, you need to simplify any repeated elements, only write them once. Okay, so another definition is, how do we know if 2 sets are equal? Well, because sets are determined by their elements, 2 sets will be equal, and I'm going to write down A equals B if and only if A and B have exactly the same elements. So they need to have exactly the same objects in both of them. The order doesn't matter. So for example, the set that contains D, E, and F is equal to the set that contains E, F, and D. Each one has exactly 3 letters and it's exactly the same letters. If I had switched one of the letters for A, then they wouldn't be equal. Another definition is equivalent sets. Equivalent sets, we represent it by like writing a squiggly line in between them. So A, line B, squiggly line B, if and only if they have the same number of elements. So when they have different objects, but the amount, the number of elements inside is the same, then we call them equivalent. They're not equal, but they're equivalent. And so we can write that mathematically by saying that n parentheses A equals n of B. So like the cardinality of A equals the cardinality of B. So the example is state whether each of the following pairs of sets are equal, equivalent, both, or neither. So if we look at A, notice that we have the letters of the vowels, only those letters that are vowels, A, E, I, O, U, and then the other sets, so separated by a comma, 3, 7, 11, 15, and 19. Each of these sets have exactly the same amount, which is 5. So in A, both of them are equivalent. So this is an example, sets that are not equal, but they're equivalent. And B, the first set has 1, 2, 3 elements, and the second one actually has 4. So these two are not equal and not equivalent. So they have different elements, and they also are not of the same amount. They're not of the same size. The amount of element, the cardinality is kind of like the size. Okay, so the next set of definitions is from section 2.2. Now we're going to talk about the complements and subsets and Venn diagrams. So let me go through. It says the universal set and the complement of a set. So we call the universal set the set that has all of the elements that are being considered in a problem. So if it's not in the universal set, it's not part of the problem. It's something that is an object that you can just disregard. So everything that we're gonna consider has to be inside of that universal set. It's gonna be denoted with the letter U for universal. The complement of a set is found by identifying those ones that are not in A. So it's kind of like the opposite. I like the word complement. I usually use the word opposite to describe it. But the idea of complement is that if you combine A and its complement, you get the whole thing. So they complement each other. They add up to the total. And it's represented by using an apostrophe on the top of the letter. We usually read it like prime. So A prime is how you're going to represent the complement of a set. Let's look at an example. So in example 1, we have our universal set consists of the numbers 1 through 10. And then S, it's a set that contains 2, 4, 6, 7. And T is the set of all X's, I'm going to say numbers, such that X is less than 10 and X is in the odd counting numbers. It's an element of the odd counting numbers. So notice that U represents the universal set and S and T are kind of like smaller subsets. So U is the largest one. So for this problem, we're only considering numbers 1 through 10. So 11, 12, negatives, 0, they should not be part of the problem, only what is inside the universal set. And in A, we're supposed to find the complement. And once again, the complement of a set, S prime or S apostrophe, it is those elements that are not in S. It's kind of like the opposite. So if you look at S contains 2, 4, 6, 7. The ones that we left out that are inside the universal but not in S would be 1, because we didn't include a 1, 3, 5, 8, 9, and 10. So the complement S apostrophe is the set is equal to the set that it has 1, 3, 5, 8, 9, and 10. So are all of those that were not in S, that were not included in S, but they're in the universal set. And the answer for B, which is what is the complement of T? Well, in this exercise, if you look at T, it's not clear what is inside T. So a good idea is to write down the list, like use the roster method. T is expressed as the set builder notation when you give a description, when you describe what is inside. So these are the numbers that are less than 10, so do not include 10. And they're odd counting numbers. So remember that the counting numbers were like 1, 2, 3, 4, 5. So these are 1, 3, 5, 7, and 9. These are our counting numbers. And then excluding, so the ones that we left outside, the ones that we did not include it in T, well, if these are the odd counting numbers less than 10, the opposite of an odd number would be an even number. So the ones that we didn't have in T are 2, 4, 6, 8, and 10. So these two are complementary because if you add them, you get the universal set. Like if you combine them, it gives you the total. Same thing for S and its complement. If you combine them, it gives you the whole list from 1 through 10. Okay, so now let's talk about subsets. I actually kind of already mentioned that a simple example would be that the set of vowels, which is A, E, O, I, U, the 5 vowels, is considered a subset of the alphabet. So a subset is kind of like a smaller, a part of the total. It's a smaller group of elements from the total amount. And the symbol that we're gonna use to represent it has, so it's kind of like a U, horizontal, and it has a line below. So whenever we see that symbol, we're gonna read it as A is a subset of B. How do you know if something is a subset of B? Well, their definition that we're gonna use is F is a subset of B if and only if every element in A is also in B. Because that's basically what it means to be a smaller portion, you know. Anything that is in A should be also contained in B because it makes B the bigger one and A the smaller, or the portion. Let's look at examples. Oh, wait, before we do examples, we have this relationship. So it says A is a subset, A is a subset of A. So this is pretty similar to when you have inequalities and you say that 2 is less than or equal than 2. So every set is a subset of itself. And in a similar way, how you have the 0 is less than any number, you could also say that the empty set is a subset of any set. So these are going to be special relationships. They are true no matter what the set A is. So it's for all sets A. If you want to say that something is not a subset, then you would just cross. We saw that before with it's not an element. So to say that something is not an element, you just put a line across. So similarly, if you put a cross, you're trying to say that it is not a subset. Okay, so the next definition is, oh wait, and explicitly, how would you prove that something is not a subset? Well, to prove that something is not a subset, what you could do is, if you find at least something that is in A, but it's not in B, then it would make it like not part of the total. Like A contains something else which is not part of B. So let's keep that in mind. Okay, so now let's look at examples. We have 4 different examples. A says that the set that has 5, 10, 15, and 20 is a subset of 0, 5, 10, 15, 20, 25, 30. True or false? Well, this statement, statement A, is actually true, huh? Because each of the numbers that are in the left, they're also in the right. So we can see that 5 is in both, 10 is in both, 15 is in both, 20 is in both of them. So each of the numbers on the left is also on the right. The next, well, this shows all of the solutions, but let me go back. Part B says that W, remember that this represents the whole numbers, and N is the natural numbers. So this statement says that the whole numbers is a subset of the natural numbers. And this statement is false because the whole numbers is a little bit bigger. This is the one that contains 0. So in this case, the statement is false because the one that is bigger is the whole numbers. So letter B is false. If it was the other way around, N subset of W, like if you change the order of the letters, then it becomes true. But the way that it's written is false. C says 246 is a subset of 246. This is true, because each of the letters on the left is also on the right. Notice that this example basically is telling you that this symbol is exactly like the less or equal. So it could be a subset that is smaller or equal at the same time. So because it's equal, it is true. And last, the empty set is a subset of 1, 2, 3. So when we look at this statement, we usually say that it is false because we're expecting to see something inside of the set 1, 2, 3. But remember that this is one of those properties that we said that it was always true. So if we go back, this is one of the main things, that the empty set is a subset of any set. It doesn't matter what the set is. And so this would be letter D is true because that's one of the properties of the empty set. So this was the answer: true, false, true, true. Okay, so this is the last part one of the last things that I want to talk about is Venn diagrams. So Venn diagrams where the name comes from the English logician John Venn, and the idea is that there's always a rectangle which encloses everything. This rectangle represents the universal set, so everything that is considered in a problem is inside that rectangle. And sets are represented typically by circles or oval regions. So the Venn diagram in the pictures shows the universal set and one set, like the set A, that is inside of the universal. Of course, usually anything that is inside, it would be considered a subset. Consider also that the size of the circle doesn't really matter. Like the size of the circle doesn't really tell you much. We're thinking that all of the elements are inside of that circle. And in this picture, the region that is outside the circle but inside the rectangle, that's the complement. Remember that the complement is everything that is inside the universal but outside of A. So the rectangle without the circle, that area is the complement. And you could think about it again, that if you add the complement plus the circle, you get the total. Okay, moving on to now proper subsets. And I think you probably noticed that when you have the equal line below, it means that they could be equal. So a proper subset should be strictly smaller. It's not allowed to be equal. So the definition would be if every element in A is also an element of B, and they're not allowed to be equal. A is not equal to B. Examples of this would be determine whether the first set is a proper subset of the second. So notice that they're separated by a comma. So in A, we have A, E, I, O, U, and then the same letters. Well, these two sets are equal, so they're not proper subsets. The set on the left is not a proper subset of the set in the right. On B, we have the natural numbers, and then we have the integer numbers. So the natural numbers are supposed to be the numbers that have from 1 all the way to infinity. And I is actually the positives, the negatives. So this statement is true because there's more objects in I. They're not equal. So the set of natural numbers is a proper subset of the set of integers. Example 4, it says, this is listing or list all of the subsets of a set. So this is a very interesting question, that if you have a set, how many subsets can you create using the elements of that set? So the set C shows the condiments that you can add into a hot dog, which could be mustard, ketchup, onions, or relish. Well, you could add more, but we're considering only these 4: mustard, ketchup, onions, and relish. So the question is, list all of the subsets of C. So when you're finding subsets, you're trying to create all of the different sets that you can have that you can create using those elements. Well, remember that the empty set is a subset of any set, so you always start by the empty set, which is basically the set that has 0 elements. Then you may consider, how many subsets of one element can I create? And because there's 4 ingredients or 4 condiments, you have 4 subsets of one element. The subset that only contains mustard, the subset that only contains ketchup, only onions, and only relish. You could think about it like maybe there's a client that uses only one of those, and so the different ways would be like, there could be one that has a hot dog with mustard, one person that only with ketchup, one person that only with onions, and one person only with relish. And you could keep on going that way, like how many subsets can you create with 2 elements? Well, all of the combinations that are displayed: mustard and ketchup, mustard and onions, mustard and relish, ketchup and onions, ketchup and relish, and onions and relish. Notice that if you change the order, it's the same set because you're using the same ingredients. So if you were to write down relish first and then comma onions, it's already been listed. So these are all of the different subsets that you can create. Next, with 3 elements, there's only 4: mustard, ketchup, onion, mustard, ketchup, relish, mustard, onions, relish, ketchup, onions, relish. And last, how many sets can you create using all 4 different elements? Well, there's only one, which is kind of like the total set: mustard, ketchup, onion, and relish. So when you're creating the subsets, you always include the set that has nothing, the empty set, and you also need to include the total thing, because it's asking for subsets. They don't need to be like proper subsets. It's asking just for subsets. So always include the empty set and also include the whole thing. Okay, so that was all of the subsets of a set. The last thing is sets, they have operations similar to numbers. The 2 common operations are the intersection and the union. The intersection of 2 sets, well, the word intersection makes reference to like streets that are crossing, like an intersection of the streets. So in a similar way, when you think of this word intersection, you should think of like, what is overlapping, like what is intersecting. And so it's representing, it looks kind of like a U that is backwards. So that symbol is going to represent A intersection B. And the definition is, this is the set of elements common to both and A. So it needs to be on both A and B. And we're going to see why we say intersection or crossing. So in set builder notation, you would say like all of the x's such that x is an element of A and x is an element of B. So these are elements that are in both A and B. Using Venn diagrams, this would be represented by the area of the overlapping circles. We can think like each point on this area is in both of them. So each point is in A and it's also in B. Okay, so an example of intersection would be if we have the set with the numbers 1, 4, 5, 7, and B 2, 3, 4, 5, 6, and C 3, 6, 9. Find A intersection B and also A intersection C. So like I said, we are thinking of those ones that are common to both, like the overlapping of these sets. So the numbers that are in both would be 4, it appears on both, and also 5. So in A, the intersection is the set that contains 4 and 5. Remember that the intersection is itself another set. So if you enter the answer on WebAssign only as 4, 5, it's going to mark it incorrect. So this is an operational set, just like numbers. When you add two numbers, you get another number. Well, similarly, when you intersect two sets, you got to get another set. So it's important to put those brackets. And in part B, we have A intersection C. If we look at the numbers that are inside A and C, we notice that there's no number that is in both. So the answer would be the empty set. Notice that you're not allowed to enter 0. You have to use that specific symbol. When you're entering this in WebAssign, you gotta click. As you click to input your answer, you'll see like a math pad, like a palette of options. You gotta find, if you click on sets, you'll find there like the symbols for the empty set, union, intersection, all of the symbols for sets. It's on that specific math pad. So make sure that you use that symbol and not the number 0. Because 0 is more of an element, this is a set. That's why it has a special symbol. Okay, and so when the intersection of two sets is empty, that means that they don't have anything in common. So in the Venn diagram, you actually draw two circles that are separate. And a better word for that would be disjoint. So two sets are set to be disjoint if the intersection is empty, if they don't have any overlapping, so they're separate pieces, you could say that. So the other operation is the union, and the union represented, again, it looks like the U, well, actually it looks a little bit different from the universal set. So also don't use the letter U if you're trying to type the union. You should be using the specific symbol, which is, you can find it on WebAssign. And this is the set of all elements that belong to A or belong to B or to both. So the way that I remember this is the word union, usually you can think about like a sum, like uniting things together, like combining things, union. And so you gotta kind of like do that union, that sum, that combination. So in Venn diagrams, this is represented with the area of the circle A plus the area of the circle B. Notice that the overlapping, the intersection, is not counted twice. So it's just like the whole area in the two circles. And an example of the union, so we have set A that contains 1, 4, 5, 7, B 2, 3, 4, 5, 6, and C 3, 6, and 9. So the union of A and B would be all of the numbers that are in one or the other. So you could start counting by adding 1, and then next 2, next 3, 4, 5, 6, 7. So actually notice that even though 5 it appears on both 4 and 5, you only count it twice. And for part B, let me just go back quickly. So A union C, notice that A has 1, 4, 5, 7, C has 3, 6, 9. Since each one of them has different elements, you just put them all together. So you'll have all 7. And usually when you look at these answers on the book, they have a tendency to write down the numbers in order. And this is kind of a good strategy just to make sure that you didn't miss any of the numbers. But the answer does not need to be in order. You could put them in whatever order. So to finish today, I'm just gonna, this is kind of like the last part of it is just to observe the connection that anytime that we use a union, the adjective and, the word and, is part of the union. So if they're asking you like, what is the set that contains maybe odd numbers and less than 10? Well, there's somehow there's kind of like an intersection there, not union, intersection. I apologize, because it has to have both of the qualities. So intersection is always associated with the word and. And in a similar way, if you have the word or, this is like a sum, like these property or this other one. So you could have both. So or is always, if you have a problem that includes the word or, then most likely the representation of that set is a union of two things, of two sets. All right, so I think I do have one more example very quickly. It says, write a sentence that describes the set. So the first one, this has like different symbols. And if you read it from left to right, this would be the set of elements that are in A, and then we see the union symbol, and because remember, well, the union symbol is or, A, that are in A, or that are in B and C. So basically, when you write it in words, you're representing the unit, you're representing the union symbol with the or, as we mentioned, and the intersection symbol with the and. Notice also that parentheses is separated with a comma. So the fact that we have elements in A, comma, that indicates that there's a parenthesis to the right. And in part B, we have, this is the set of elements that are in J, and then we have the intersection symbol. So we need to say that are in J and that they're also not in K, because even though we have the K, we also have the prime, which is the complement. So this is the set of elements that are in J and not in K. Okay, so this was my last example. Thank you so much, everybody, for attending, and I hope you have a great Friday. And I'm gonna give back the command to the host.
Well, thank you so much, Mr. Tinto, for presenting today, and thank you all for coming and being such a wonderful audience. And we definitely hope to see you soon again. And please, yes, I was going to do that. And please, yes, I was going to do that. Please, so join us next week. And if you look at the flyer right there on your screen, you'll see that for February 6th, we'll be covering for Math 1332, application of sets and exam 1 review, and for Math 2412, inverse trigonometry functions. So we really hope to see you then. Have an amazing weekend, guys, and thank you again. Bye-bye.